To introduce this keynote, I'm really glad to welcome Louis Delannoy and Hugo Le Boulzec this morning. So Louis Delannoy is a postdoctoral researcher. He doesn't make my task easy because he's part of two groups of two different labs. So he's part of the Global Economic Dynamics and Biosphere program of the Royal Society, Swedish Academics and the Stockholm Resilience Center. So here is Louis. Louis examines how multiple environmental and social shocks interact to create systemic crises. And Louis is also a local, as he obtained his PhD in applied mathematics from University of Grenoble, in which he explored systemic risks emerging from interaction between energy, finance, and economy. So welcome, Louis. Hugo Le Boulzec is also a postdoctoral researcher in the Grenoble Applied Economic Laboratory on the modeling of co-benefits and risks on energy systems and air quality, I would say. His research focuses on raw material for the socio-ecological transition as well as on modeling practices. From what I heard in the past few days, I think you'll find this keynote, well, I hope you'll find this keynote very interesting. I really think this will be food for thought as it will introduce a conceptual framework for a tricky question, how to take into account biophysical constraint in our modeling. So Hugo, Louis, the floor is yours.
So a bit of context before starting the presentation. So first, thank you, Sacha, Etienne, and Sébastien for the conference and the organizing committee for the conference. And thank you for the opportunity to present this keynote. We're really glad with Louis to be able to do so. It was a tough process to elaborate the presentation since you'll see it's very wide. And we try to bring it back to the energy system thematics for the energy system models community. And this is really an ongoing process, an ongoing thinking on why and how should the integrated modeling evolve, and why we may need some new tools to do so. So this presentation follows on a breakout group of last year Open Mod workshop in Vienna that we co-animated with Sacha on energy modeling and critical thinking. And you'll see that for those who followed the speech by Richard Thompson a bit earlier this year, we're not escaping from model land, but we're trying to think about what it could and should become in the future. This is very ambitious, we know it, but we rather see this presentation as a call for discussion and more collaboration between communities. And so we have some insight to share. And any on our tools and approaches would be inconsistent and not possible, not feasible, without the involvement of many other communities. So this is the forward. Thank you. So we've entitled our presentation Contrasted Modeling for a Constrained World. So first, we'll focus on the constrained world aspect. So at first, we want to show you some news that were published in the recent months and years. On the top left, you can see a closure of a mine, copper mine in Panama because of environmental and institutional reasons. And the mine represented about 1%.
Stay close to the mic.
Okay, for the recording?
Exactly.
Okay. I wanted to work, it's okay, too bad. And so the mine represented about 1% of the global copper production. Then on the top right, you have a news by UNICEF about the drought in Zambia, which had severe consequences on energy systems since the country relies a lot on hydropower for its energy mix. And it's up in the valley where there's about 40 to 50% of the country population. So it has many impact also on local systems. Then on the bottom left, you have quite similar news on drought in China, which had many consequences on the shift from hydropower to coal power because of climate conditions. And then on the bottom right, you have a more political and social news about the fading enthusiasm of the Swedish people for more onshore wind farms at the national level. So you could ask, what are the links between those news? And that's why we're trying to figure out. So here is some proposals, some practical exercise to link these news. So let's consider a wind turbine that we want to implement in Sweden. So the journey of this wind turbine starts from a mine, for example, copper production. So this is a hierarchy graph on copper ore and concentrates main producing countries. And we can see that it's mostly in Chile, Peru, Congo, and other countries. And what's interesting is that when you see the news that we've shown in the previous slide, you have like this emergency, the drought in Zambia, which has impact on the potential energy supply of Zambia, and so on the ability of the country to produce copper. And the country produces about 4% of global copper production, so there could be impact. Then you have the Panama mine, which closed, and it represented about 1% of the global copper production. And finally, you have a water scarcity in Chile, and a race by the mining industry to find more water. They need more water for the processes. And they go in toward more desalinization, which requires a lot more energy than usual water. So there are constraints at different scales and different times between different subsystems, energy, resources, etc. Then once you have the copper ore, you have to refine it. So then you go in other countries, for example, China, which is the main producer of refined copper. And in China, refining copper needs a lot of energy, which impact is dependent on the energy mix. So basically, if because of droughts you have less hydropower and more coal, the producing copper could have more impact in the long term because of climate-related constraints. And then once you have the refined copper, you have to manufacture it toward final products. So many different firms achieve this task, and the main one is Vestas wind system. And it has many different manufacturing locations around the world in many different continents with many different social and political constraints and energy mixes, so different impact. And what we also observe in the last month and years is financial difficulties of this sector because of a lack of approval for new wind farms. So these players could also potentially be at risk. And finally, once you've got the wind turbine, you have to implement it. But you have local social constraints on the acceptance of wind turbine in territories. So for example, in Sweden, you have recent constraints on the political enthusiasm for onshore wind turbines. So what we want to show you by this process of implementing a wind turbine is that finally implementing a wind turbine depends on many other constraints and many other possibilities at different scales. So in both time, because opening a mine, producing a wind turbine, refining copper has different time scales and different also space. So it can be local territories with local subsystems, with water, energy, and local population, but also global constraints, so climate conditions. And so if we want to try to split the constraints in two categories, we could see structural constraints, which are long-term constraints, foreseeable, and they force actors to plan strategies to avoid being faced with those constraints. It can be climate conditions, the mid-transition, for example, for energy systems, the network constraints, but also energy resource quality, for example, the EROI that we will tell you about in a few minutes. And then you also have temporary constraints. So they have like short-term aspect, they are hardly foreseeable, and they force actors for emergency response. So we saw this with COVID-19, for example, with the pandemic. So this can be geopolitical constraints, but also drought or supply chain disruption. So what's important for us, in our opinion, is the different scales in time and space to face those constraints.
So now that we've covered what we understand as the basics of what are constraints, let's attach a bit of formalism to our analysis. So if you place the energy system as the core of society, you will soon realize that its proper functioning is governed and governs other systems such as materials, water, land use, climate, the economy, and population, themselves connected. For instance, the energy allows the production and exchange of services and goods, and the energy production is itself depending on economic factors. So let's get into two different constraints here in a bit more detail. Let's focus first on the energy required for the materials extraction, and then we'll briefly discuss the energy required for the proper functioning of the energy system itself. So you might be aware that the mining industry final energy consumption, so in dark blue on the left side, so it's estimated through a bottom-up approach, and it's compared to the IEA value, which is like relying on national estimates given by governments, so that's why it can be a bit less reliable. It also do not encompasses indirect energy cost, so there is a discrepancy in between the two. You can see that this energy consumption rises since the 1970s, and quite trivially, because we are extracting more and more materials. And if you plot that energy over like the total energy consumed, you will see that it's a tiny constraint actually, from a bit more than 1% in 1970 to a bit more than 1.6% in 2016. However, that might change in the future because we are approaching thermodynamic limits against which technological improvements cannot counter the fact that mineral ore grades decline. I won't go in detail on the figure on the left because it's not super practical, but I just wanted to show you for one line in this figure. It is the black one, which decreases, and starting from 2030, that line increases. This is the energy required to extract minerals, and I think this example is for copper. And as a result of that, the energy needed for the mineral industry is likely to increase by 2 to 8 times by 2060. And now if you consider the energy system as a whole, and for instance, let's take the oil industry, you have the same dynamic, meaning that mankind tends to actually deplete resources and that we go after resources that are more and more energy intensive. Here, for oil liquids, that could be biofuels, that could be mine shed oil, that could be coal to liquids. And they require more and more energy. And if you aggregate all of this energy, you obtain this orange curve at the top, the energy required to produce energy, which is what is needed to produce all what's below. And you see that today this is approximately 16% of the total production, but that might rise to 50% in 2050, which is a huge constraint for the oil industry. So taking this energy system now, if you implement an energy scenario which is quite utopic, but in line with the 1.5 degree objective of the Paris Agreement, so with an enormous rise in renewables, you will see that the energy consumed by the energy system increases from approximately 12% in 2019 to 33% by 2035, which is huge. But like, you need energy to build and operate wind turbines, solar panels, batteries. It's an investment, right? That's why it decreases shortly after. So why do these constraints matter? So if you implement them into a single framework and compare their impact, so for instance here you have the reference scenario top left, so with like all the constraints. Top right, you remove the energy availability constraints, approximately what we saw in the focus number 2. Below left, there is no climate change damage constraints, and below right, no constraints at all. You see that energy mixes actually change drastically if you consider not constraints. That's why they matter, shortly. And before I venture to the next slide, I would just like to ask you who here is aware of what is an IM for Integrated Assessment Model? And you can raise your hand, please. And who is handy or has been working with an IM? 1, 2, 2.5? Okay. Okay, so for, I think still the majority of people that do not know what IMs are, IMs are those big, really main tools used to produce global disaggregated mitigation pathways. And to do so, they integrate different constraints into the systems we saw before. But as you might all be aware, the modeler's curse is that the expectation can be quite different from the reality, meaning that at the beginning, you might want to connect everything, think deep about the dynamics that would result from that. But at the end of the day, high are the chances that you have like only big boxes connected. So what to do then, and how to integrate constraints?
Okay, so to try providing some insight for this question, we want to provide you with some recent thoughts and works. So this is an ongoing tryout conducted mostly in Grenoble, but in collaboration with other teams in Cambridge and in Leeds. So only the two of us today, but many other people working on the project. And so by contrasted modeling, we want to describe a process toward a more integrated and dynamic approach of numerical modeling for global thematics with a more reflexive approach on why and how do we model subsystems. So first, I would like to get back to the process, the framework of modeling for integrated modeling. So it starts from, on the left, quantitative narratives about education, about technological progress, about inequality, equality, with regional differences. It feeds into an economic model, which is developed by the OECD. It's called ENV Growth, and it provides integrated modelers with SSP scenario, which are basically GDP per capita and population provided by another model. Then the YAM community establish energy climate scenarios depending on climate conditions. And sometimes you have feedback from the climate impact on the economic part of the YAM. So it's basically not bottom-up impact, mostly top-down impact. So on the right, the dashed arrow. And so, for example, impact per point of GDP. So this linear process is also the case for communities. So recent research showed that the communities are working one after the other, and it could explain, based on different research works, an inconsistency between scenarios and model. What we also see in this sketch is that we first assume a socioeconomic condition system, and then we try to estimate what technical solutions could provide, could allow to stay within some climate constraints. We want to assume the opposite in our research approach. So this pyramid shows the hierarchy from bottom to top of our approach of constraints. So first, we assume that biophysical constraints, so meaning thermodynamic limits of resources exploitation, extraction, water depletion, and etc., are the first constraints to build on a society. So then, on top of these biophysical constraints, we can organize ourselves as a society in many different ways. So this is a choice. And this choice has to stay within the biophysical constraints, in our opinion. So then once we have designed a socioeconomic constraint, so far we're living in a socioeconomic system which is a choice from the past, and we assume that it will continue this way in trend modeling, but it could be different. And then on top of these socioeconomic constraints, you have technical constraints, basically, so what mixes of technology could allow to achieve and to fulfill the services that we all need on a daily basis. So mobility, housing, etc. And it depends on market regulations, on policy, and etc. So it can seem very theoretical, and what we try to do now is to build on a model, so a numerical model, to try modeling things this way. So the model is called the MATER framework for multi-scale assessment of technologies, energy and resources, and it's grounded in industrial ecology, ecological economics, and social metabolism. And the central thought of our approach is that nothing is given for free. So anytime you have a process in a human society, it consumes resources, goods, and it produces impact. This is the central part of our approach. So to properly estimate the impact and the links between the resources and the good, we think we need a bottom-up approach. So downscaling the systems to a car, to a square meter of housing, and etc. So on the right, I can see that you all already watching the sketch. This is a sketch of what of our model. It's voluntarily oriented on resources and technology for this presentation, but it will focus on other things. So to describe the model, I will take an example. So on the bottom, let's assume a mobility service in Sweden, to stay in Sweden. So for example, a number of kilometers we want to do a year. So we need a technology, a good, which is a car. So this car, basically, what's central, the first central part is that it has inflows. So the car is a stock. It's an in-use stock currently used for a service. The horizontal lines show what goes into this stock and what goes out. So on the right, you have an inflow, which is the number of new cars produced, which goes into the stock. So we need to build cars to use them. And then on the right, you have outflows, which depends on lifetime. So a car, for example, has a lifetime of about 12 years. So you have cars outflowing the stock every 12 years, about 12 years. Then the vertical arrows show what we need, what resources and goods we need to actually use this car. So we need electricity for an electric car, but we could need oil for a thermal car. And then there is impact. There are impacts. So air pollutants, greenhouse gases, etc. But what's important for us is the double consistency within this stock and flow. So any flows produced by a stock has to come from another stock, another elements. So for example, the car is produced by a manufacturing plant. This manufacturing plant to produce the car requires energy, raw materials, and has impact. To produce the energy required to use the car, we also need energy which is produced by a power plant. So this exogenous constraint, a need for mobility, creates a diffusion so in the model. So you have, given that nothing is given for free, you have like a cascading effect in the model because anything you use will produce impact and need resources and goods. So it goes also for, it applies also for power plants. We need raw materials to produce power plants. We need a manufacturing plant to produce power plants, etc. So, of course, such an approach would require a significant amount of data, and we're aware that this is very hard to display, to build, but we've chosen completitiveness over accuracy. We think that there are many constraints that should not be taken into account while taking these systems more accurately, but separately. So we need to integrate them into one framework. What next? Sorry. Yeah, that's it.
Okay, so to conclude this keynote, I would just like to share with you a few thoughts on our approach then that we term contrasted modeling. It encompasses actually quite a few advantages and drawbacks. And to begin with, I would really like to stress that this type of modeling is quite intensive, both brain-wise and, you can mention it, data-wise. And we have quite a challenging time in order to integrate like one constraint after the other and really think about the proper way to ensure consistency in between everything we do. Another drawback is, and I think it's something that we need to speak about, transdisciplinary is freaking hard. Sometimes we interact with people from different fields and we have really a hard time understanding each other. And still, we need transdisciplinary in order to have a consistent model that also speaks to different communities, right? And on kind of a related note, there is a risk of this approach being too heterodox, meaning that it is not conventional, so that there might be some people for who that approach could be too different from what they do, and then you might have a hard time speaking to each other. Yet, it also has like quite a few advantages. The first one is, of course, that we ensure consistency in between input and output. At least we really aim to and try to do that every time. The second one is that it's quite modular and quite flexible. You can adapt this modeling to a few different research questions. And the last advantage is really that it is much heterodox. And that's a good point. We need radical alternative modeling frameworks. We discussed, and I think we'll discuss as well a bit after, why the current crop of IAMs are somewhat kind of limited, and especially when it comes to prefigure the polycrisis and the inner roots of these polycrisis. And on that note, I thank you very much for your attention and shoot any question you have.